Welcome back to ECE 501B. Before we went on air, I was informed that I had a disconnect with my deadline date for deliverable number 1 for the project. I've been corrected. It should be the 17th of November, which gives you a few more days to ponder and reflect about what you want to do for your project in this class. And the other two deliverables, which is really the meat of the project, that's due on the last day of class, the 7th of December. So if you haven't yet given me something with respect to the project, the deliverable date has been advanced into the future by 10 days versus what I had been advertising in maybe some previous lectures. Homework number 7, which isn't even posted yet, is due on the 30th, and homework number 8, so you see we only have 2 more homework assignments. That gives you more time to work on your project by the end of the semester. What I want to do today is continue with operators on inner product spaces, which is chapter 7, and in particular pick up with this concept of an operator being normal. That's not in contrast to it being weird, but normal means that it has certain properties, or yes, I would say characteristics that it possesses, and one is that it sort of preserves this norm. And we'll prove that in our first part of today's class, that the norm of TV is equal to the norm of the adjoint operating on V for all V, and we'll show that T dagger minus T dagger T, which is really equal to 0 when it's normal, that particular operator is self-adjoint. And then we'll look at some properties of normal operators, and in particular corollaries 21 and 22, which talk about how these eigenvalues and eigenvectors of the operator T and its adjoint are related, and also that distinct eigenvalues, when we have a normal operator, actually yield orthogonal eigenvectors. And maybe that sounds somewhat like one of your problems on exam number 2, maybe not. Then we will get into where we were trying to reach before, and that's spectral theorems. And it pertains, or it really is dependent on the underlying space that we're working on, and so we'll look at those two different spectral theorems separately. We'll look at the complex inner product space, and in that inner product space, when it's complex, if our operator is normal, then we have an orthonormal basis, and that allows us now to diagonalize the operator, which is this nice property that we're looking for. And when we're dealing with a real inner product space, we have to narrow down what we allow, or what allows us to yield an orthonormal basis, and that's to require that the operator is not normal, but actually more narrow and is self-adjoint, which means that T is equal to its dagger. When it's normal, that just means that T and its adjoint commute. And that's not quite as restrictive as it being self-adjoint. And actually, before we get into the real inner product space spectral theorem, we'll have to pick up some of the background information, which is remind ourselves about the Cauchy-Schwarz inequality, which was in chapter 6. We'll talk about completing the square, which you've done in your algebra classes in earlier offerings of math, which is probably pre-college. And then we will talk about some lemmas, and in particular lemmas 26 and 27. And 27 says that if this operator is self-adjoint, then we know that it has an eigenvalue. And in lemma 26 in chapter 7, this particular operator, which looks like a quadratic form, t squared plus alpha t plus beta I, as long as alpha and beta have certain relationships, that operator is invertible. And when is an operator not invertible? When it has a non-trivial null space, or when it's not surjective. So we have these properties holding when this particular operator has a certain relationship on alpha and beta. Then we have an injective operator, a surjective operator, which means that we now have this isomorphism between the input space and the output space, or that operator is invertible. Let's now start with this relationship on the operator and its adjoint, which is proposition 20, and that now says that T is normal if and only if the norm of TV is equal to the norm of T dagger V. Because of this if and only if, now if you can show that T is normal, you know this norm relationship is true, or if you can show this norm relationship is true, you can then conclude that your operator is normal. But this says then an operator T is normal if and only if these two norms are equivalent for all V. And let's now show how that comes about. If we look at T and its normal, that now means that the operator and its adjoint commute. Or we can say then that T dagger is equal to T dagger T. But that really can be written as, if we move one of those to the other side, we can say then that T being normal is equivalent to T dagger T minus T dagger being equal to the zero vector, or the zero operator, I should say. If we now use that as our zero operator, we can now form an inner product. We can now say that the inner product in the first slot of that inner product, let's say we have T dagger T minus T dagger operating on a vector V. And now in the second slot, let's keep that same vector V. If we now recognize that this is now the zero operator, what do we know is the result of that inner product? We know that's going to give us a scalar zero, a zero scalar. And that's true for all vectors in our underlying vector space. Since if T is normal, then we can make this conclusion. Because if T is normal, then we know that T dagger T minus T dagger is the zero operator, and the zero vector inner product with any vector is giving us zero. That's one of our results. Now we can start playing with these properties of inner product. For example, if we now look at or apply additivity of the first slot, that now allows us to distribute those two terms into and separate this one inner product into two inner products, where we now have T dagger T times V, and we can actually associate or group those however we want with V. That's the first part of that additivity of the first slot, minus the inner product of T, now T dagger V, inner product with V, and that's now equal to 0 for all V in our underlying vector space. I really haven't done anything except manipulated that initial inner product expression. I've just now pushed it or broken it or separated it into two different inner products. Now what we want to do is use or apply the definition of the adjoint. if I apply the adjoint definition to the first inner product, and let's keep that parenthetical vector TV on the left or in the first slot, now what is that inner product equal to relative to the definition of the adjoint? If I now have TV in the first slot for this leftmost inner product, what's in the second slot? It's the adjoint of the operator that was applied to TV. Or we now have T dagger dagger applied to V. That's the definition of the adjoint. But that actually allows us to simplify. This is now what? What's T dagger dagger? That's just T. Now, if we do the same thing to the second inner product in the blue line, now we have T dagger V in the first slot, and in the second slot we have the adjoint of T, which we've been denoting as T dagger. That's T dagger V, and that's equal to 0, again for all V in the vector space. And what does this now allow us to do? Now we can say that we have this TV inner product with itself in the left, and on the right we have T dagger V inner product with itself equaling 0. But we know another way of writing that particular kind of inner product, since it's what's in the first slot is in the second slot. That's now just the norm squared. Or we now have the norm squared of TV minus the norm squared of T dagger V. Let's just put that one on the other side, and we can now say that the norm squared of TV is the same as the norm squared of T dagger V for all vectors in our vector space. And we were able to show that simply by relying on the fact that our operator T was normal. So the fact that T was normal now allowed us to keep these two norm relationships the same, or to have equality between those two norms. One thing that we can also observe before we go any further is that the operator made up of the following: T dagger T minus T T dagger is actually self-adjoint. And all we really have to do to show that is to remember what happens when we start taking the adjoint of operators or combinations of operators. Here, let's say that we take the adjoint of what's in parentheses. Now we can separate that into two pieces. We have T dagger T dagger minus T T dagger dagger. Can we have any more daggers? We're a little bit beyond Halloween, but we're a week late, but we still have some daggers. Now, what happens when I have an operator, two operators, and I take their adjoint in terms of their orientation or their relationship with each other? Is that too vague? They interchange places. So that now, in terms of the first piece of this, I now have to, if I now take the adjoint of T dagger T, I now really have the second term adjointed, which was t, so I adjoint t, and then I take the first term, which was t dagger, and adjoint that. Minus, and if I do the same thing for the second one, I now take the second term and make it the first operator, and dagger it, and then dagger the first operator and make it the second in that combination of operators. Or I now have t dagger, and t dagger dagger is t, minus t dagger, and that's what I intended to show. That in fact, that parenthetical operator, when its adjoint is found, is equal to that parenthetical operator. Or t dagger t minus t dagger is in fact normal. Or I should say self-adjoint. Okay? It's more than normal, it's self-adjoint. And that's what we just showed. That the operator is equal to its adjoint. Let's now look at, now that we have those available to us, let's look at some properties of when an operator is normal. Properties of t being normal. And let me state those, and then we'll talk about them more formally. The first one is that we want to see if there's any kind of relationship between eigenvalues and eigenvectors of the operator t and its adjoint. And we also want to talk about what happens when we now have distinct eigenvalues of an operator, and we will show that that actually gives rise to orthogonal eigenvectors. But before we get even into those, let's look at a relationship or a lemma that we need or that we can use to help us work through these particular facts or properties dealing with an operator being normal. Or prior to stating and proving corollary 21 in chapter 7, let's verify the following lemma. Where the lemma says that if we have an operator t and it's normal, then the operator t minus lambda I is also normal. And now, in order to show that something is normal, we need to show that the operator and its adjoint commute. Or now we want to show that t minus lambda I operating on t minus the adjoint of t minus lambda I is equivalent to or the same as the adjoint of t minus lambda I operating on t minus lambda I. where we're now showing that t minus lambda I commutes with its adjoint. Let's now expand the left-hand side, and then we'll expand the right-hand side and show that we get the same terms. And then we'll know that they're equal. If we look at the left-hand side, again, we're just playing with applying the adjoint to a succession of operators. T minus lambda I operating on t minus lambda i's adjoint. First, let's take the adjoint inside that second operator, and we have t minus lambda I. And what happens when we adjoint this scaled version of the identity? The adjoint of t is just going to be t adjoint, but what's the adjoint of lambda I? It's the conjugate of lambda times the identity operator. So we now have lambda star I. And we can now form that product of operators. We have t times t dagger minus lambda I times t dagger, applying that first operator to the first operator in the second set. Then we have minus t times lambda star I plus lambda star I, since I times I is the identity map. And we can now clean that up just a little bit by factoring out the scalars and removing the identity operators, so that we now have t dagger minus lambda t dagger minus lambda star t plus, and what do we obtain when we have a scalar times its conjugate? Now we just have the magnitude of that complex number squared, scaling our identity map. That's what the left-hand side in this equality provides or yields. Let's now look at the right-hand side, which is t minus lambda I dagger times t minus lambda I, and hope that it gives us the exact same expression that we just derived. In this case now, the right-hand side produces or starts with t minus lambda i's adjoint applied to t minus lambda I. Again, we can push that adjoint through to the both terms, and we have t dagger minus the conjugate of lambda times I times t minus lambda I. Or we now have t dagger t minus lambda star t. Well, maybe I should do all the steps that I had done before. And now I have minus t dagger. I'm just trying to mess up my t dagger times lambda I plus lambda star lambda I. And what I want to do next, since it looks like that very first term is not the same in the black and the blue, but what do I know about t? What was the very first assumption that we were assuming in this lemma? We said t was normal, which now says that t commutes with its adjoint so that the first two terms can be equal. Meaning, let me now take the first term in the black or the right-hand side and say that's t dagger by simply using the fact that we were assuming that the operator was normal. Then we have minus lambda star t minus lambda t dagger plus the norm of lambda squared I. And hopefully that looks like the blue. It's just that the middle two terms have been interchanged, but they're exactly the same two terms. Which means then if we have our operator is normal, then we know that t minus lambda I is normal. And if t minus lambda I is normal, we can start looking at using that earlier relationship was this equality of norms. And that's what we want to use in this next corollary. The corollary that we want to talk about now is given an operator t on the vector space V is normal, if we have a vector V in the vector space and it's actually an eigenvector, of our operator t with eigenvalue lambda, in our field, then in fact this vector V that was the eigenvector of t is also an eigenvector of the adjoint of t. Then V is also an eigenvector of the adjoint of t, and the eigenvalue is the complex conjugate of the eigenvalue of the operator t. Let's see if we can demonstrate that. Let's take V and lambda as the eigenvector eigenvalue of t, which really means that lambda and V satisfy the eigenvalue-eigenvector relationship, which is TV is equal to lambda V. If TV is equal to lambda V, we can rewrite that as T minus lambda I applied to V is the zero vector. And now we know something about T minus lambda I. In this particular corollary, we're assuming that T is normal. And if T is normal, we know that the operator T minus lambda I is normal from the above limit. Since we've assumed T was normal. But once we know that we have T minus lambda I being normal, then we can use the first proposition that we talked about today, which was this norm relationship on operators and its adjoint. Now we know that this norm of T minus lambda I applied to V is equal to what applied to the same V? The adjoint of T minus lambda I. We know those norms are equal. But what do we know about t minus lambda I times v if lambda is an eigenvalue and v is an eigenvector? In the top right-hand corner of the screen, we know that that's 0. So this is, in fact, the norm of a 0 vector, which is 0. But that now applies to the t minus lambda I dagger norm when applied to v. And that now allows us to conclude that the vector didn't change, so v is in fact an eigenvector of t dagger, and its eigenvalue excuse me, is going to be the adjoint applied to a scalar, lambda, which is the adjoint, or which is the conjugate. So v is an eigenvector of t dagger with an eigenvalue of the conjugate of the original eigenvalue of t. And that's because since the norm of t minus lambda I dagger v is 0, we know that that's the 0 vector, so that now we have tv, or t dagger v, minus lambda star v as a relationship. And that's the eigenvalue-eigenvector relationship of that operator, which is the operator t dagger. Which now says that if we have a normal operator and somebody's interested in the eigenvectors of that operator, and maybe they're interested in the adjoints eigenvectors, those will be the same, and their eigenvalues will be conjugates of each other. That's if t is normal. Let's look at what happens to the relationship between eigenvectors when we have distinct eigenvalues when we have a normal operator. This is now corollary 22, which says that given t, a linear operator on a vector space V, and its normal, the eigenvectors of t corresponding to distinct eigenvalues are in fact orthogonal. So an operator being normal gives us some pretty nice properties relative to eigenvalues and eigenvectors. Proof. Suppose we take two scalars, alpha and beta, and let's just assume that those are our distinct eigenvalues of our operator t. Whoops. And we want the eigenvectors of those eigenvalues to be u and v. In other words, if we have tu, I'm saying that that's going to give us a scaled version of u with the scaling being determined by the eigenvalue alpha. And if we now look at the operator t applied to the eigenvector v, that's going to give us a scaled version of that eigenvector with the scaling being the eigenvalue beta. Let's now build a inner product. Suppose that we now create the following. We take the scalar, alpha minus beta, and let's apply that now to the inner product of u and v. We can now distribute those scalars relative to that inner product, and we can now say we have alpha applied to the inner product of u and v minus beta times the inner product of u and v. Let's suppose now that we slide that scalar on the first inner product into the first slot. And it slides without change because of the homogeneity of our first slot. Or we now have alpha u inner product with v. What if we take the second inner product and slide that scalar into the second slot? What happens to beta? With a conjugate, right? And what does the first inner product actually yield when we realize what alpha u could be written equivalently with? U was an eigenvector, alpha was its eigenvalue, so that's the same as t applied to u, operate in the first slot, and in the second slot we have v. We can do something similar with the complex conjugate of beta applied to v. We now know that that would be t dagger applied to v. But the definition of the adjoint allows us to write this in what way? That's now just moving that operator into the other slot. We can take its adjoint, and we now have tu inner product with v. So that now we've ended up with the inner product of tu with v, and take that away. So we have the scalar minus the scalar. That is now equal to 0, and we were able to conclude that by using the definition of the adjoint on that second term. Or, now that that's equal to 0, whatever we started with was actually equal to 0, which was this scalar alpha minus beta times the inner product of u and v. Now we can say that that is 0. So now we can say that alpha minus beta times the inner product of u with v is equal to 0. But what did we assume about alpha and beta? Did we say they were the same? No, we said they were distinct. Since alpha and beta are distinct, now we know that this scalar alpha minus beta is not 0. We can divide it out, and that allows us now to say that the inner product of u with v is equal to 0. And if we have two vectors whose inner product are equal to 0, what does that allow us to say about those two vectors? Those two vectors are orthogonal. And that's what we set out to prove. Now we're in a position to talk about spectral theorems, which is really this nice property of operators, or when can we diagonalize operators? Because if we can diagonalize operators, then it's easier to think about what's going on or what we have to play with. So let me start writing or commenting on some of that. We are going to be now talking about the spectral theorem, which really we will have two different theorems, one for complex inner product spaces and one for real inner product spaces. We now come to see, or we come to the end, of our quest or journey to find what we were labeling nice basis for a given vector space. And what we are wanting to do is remember the appeal of diagonal matrix representations. What do we know about those diagonal elements if we do have a diagonal matrix? They're eigenvalues. And now we have this ability to say something about invariance of subspaces relative to diagonal matrix representations. Remember also that an operator only has a diagonal representation if there exists a basis consisting of eigenvectors of the operator. So if we can find an operator that has eigenvectors that make a basis, then we could diagonalize that operator. What we want to do now is actually further specialize that now that we've introduced this idea of inner products. Now we can normalize those eigenvectors. We'll add a further constraint that we'd like not only normalized but orthonormal basis. So we must be in an inner product space. And the spectral theorem tells us which operators have eigenvectors that can produce such an orthonormal basis, and therefore which operators have a nice diagonal representation. And the answer that we will come up with actually depends on whether we're working with a real or complex inner product space. The answer depends as far as what we can say about these operators. The answer depends on whether we are dealing with a real or complex inner product space. And because of that, we'll look at these separately. Let's look at the complex case because it's actually easier than the real case, or the spectral theorem in the complex inner product space is actually a little cleaner than that in the real inner product space. And this is now theorem 24 in chapter 7, and that's called, obviously enough, the complex spectral theorem. Suppose we are dealing then with over the field of complex numbers. Suppose F is our complex field, and we have an operator on the inner product space or the vector space V. Then we can actually show equivalence of the following three statements. Then the following statements are equivalent. 1, T is normal. So if we have a normal operator, then that's the same as the next two statements. The second statement says that our vector space V has an orthonormal basis and those basis vectors actually consist of the eigenvectors of our operator T. If we have an operator and it's normal, then we can say that we can actually create an orthonormal basis on our vector space V out of the eigenvectors of that operator. C says that we can actually form a diagonal matrix. So T has a diagonal matrix representation or has a diagonal matrix with respect to some orthonormal basis of T. If we have three statements that are supposed to be equivalent, what's one way of showing that? We could show A implies B, B implies C, and C implies A, right? Or we could show A is equivalent to B, A if and only if B, B is equivalent to C, and we'd be done. But the textbook actually says that if we go back to chapter 5, we already have a way of showing the equivalence of B and C. So B is equivalent to C from proposition 41 in chapter 5, which that one was dealing with the equivalent conditions for an operator to be diagonalizable. So let me say equivalent conditions for diagonalizability. Or in other words, let's not show B if and only if C. Let's just show that A is equivalent to C, and then we'll be good. So let's start with this equivalence of A is equivalent to C by showing that C implies A. And then we'll need to show that A implies C, to show that A and C are equivalent. So to show that C implies A, let's say C implies A is now our first part of this proof. Let's assume that we have statement C being true, or T has a diagonal matrix with respect to some orthonormal basis of that operator. And then we need to show that that operator is normal. Assume V has an orthonormal basis of eigenvectors of the operator T. And if we are assuming orthonormal, we now have a way of normalizing or talking about norms, so we now have an inner product space. If we now have an orthonormal basis of eigenvectors, then we can actually diagonalize the matrix representation of T, and we know that from an earlier proposition in chapter 5, which is proposition 521, that says T then has a diagonal matrix representation with respect to this basis, this orthonormal basis that we're assuming. If T now, that operator, has a diagonal matrix representation, what do we know about the matrix representation of the adjoint of T? How is the matrix representation of T related to the matrix representation of its adjoint? Those are related by this complex conjugate transpose relationship. So now we have the matrix representation of T dagger is the conjugate transpose of the matrix representation of T. But the matrix representation of T is diagonal. What happens when we transpose a diagonal? Not much exciting, does it? We get back the same matrix. So we now know that the matrix representation of the adjoint of T is also diagonal. Therefore, T dagger also has a diagonal representation with respect to this basis. And let's just remind ourselves what happens when we're dealing with diagonal matrices and we want to take those in combination. Or let's consider the product of two diagonal matrices. Now I'm definitely assuming that we're late on a Monday afternoon. This shouldn't be hard to do. We're just going to multiply two diagonal matrices. Pardon? So now it's just going to be the product of the entries on the diagonal, isn't it? We now have, let's say that we've now taken two matrices that are diagonal. We multiply those together. A1, or the first row in the left matrix, is going to scale the first row in the second matrix, and it's scaling by A1. And there's only one non-zero entry in the first row in the second matrix, so we now have A1, B1. A2 is scaling the second row, so that we now have A2, B2. Or if you wanted to, you could act on the columns in the second matrix, and you could say, oh, B1 is actually going to scale the first column in the first matrix by B1. Either way, you're going to end up with the only non-zero entries are on the diagonal, and those non-zero entries are the product of the original diagonal entries. And I think you can see that you're going to get exactly the same product or result if we commuted those diagonal matrices. We get the same structure or form when we take B1, B2, B sub n as a diagonal matrix and apply that to the diagonal matrix with A's on the diagonal. Here we have B1, A1 if we wanted to preserve the order of the multiplication, but these are now simply scalars, and they can then slide through if we want, and so the right-hand side, or the product, is the same in both A times B and B times A when those are diagonal. Since any two diagonal matrices commute, it follows that. And what were those matrices? Well, they were, in this example, those were the representations of the operator T and its adjoint, since we knew that they were both had diagonal matrix representations. That says then that if we applied T to T dagger, that's going to be the same as T dagger applied to T. But that relationship now says the operator and its adjoint commute, which allows us to conclude statement A, that the operator T is in fact normal, since it satisfies that relationship. That was half of this equality. That showed that C implies A. If we look at the other direction, which is for A to imply C, now we're starting with the operator being normal, so that now we're assuming that the operator T is normal. If the operator T is normal, then we know that T actually has an upper triangular representation. In fact, that's true for any operator since we're on a complex vector space. So that statement is not really saying too much or assuming much. We can have an upper triangular representation of an operator T on a complex vector space. So that's true for any operator on a complex vector space. And that's theorem 38 in chapter 6. If that's the case, then we can think of the matrix representation of T on some basis E1, E2 through E sub n. If it's upper triangular, let's now just say that that's going to be A11, A22, all the way down to A sub n, and now we have A12, A13, etc. to A1n, A23 to A2n, and 0 below the diagonal. And we can do that with this basis actually being orthonormal. Now from this representation, we can actually conclude that if we look at this matrix representation of our operator T applied to E1, that's now A11, A12, A1n, A22, 0 below the diagonal, A sub nn, times E1. But if we now looked at a special kind of E1, an orthonormal basis, one such vector would be 1 in the first coordinate and 0 everywhere else. If that's the case, what do we get for the result? That's just going to pull off the first column in that upper triangular matrix, which is A11 and nothing else. But that is a scaled version of that orthonormal basis, 1 with zeros below it. And what have we concluded then for that particular choice of E sub 1? What do we call such a vector E sub 1? What happens when we hit that E1 with this matrix representation of T? Where do we move? Really nowhere. We go back to that same subspace or that vector. So it's invariant. Now we have an invariant subspace, and that's the definition of an eigenvector. So that now E1, this particular E1, is invariant with respect to T. Which means then if we wanted to look at the norm squared of T applied to E1, that vector, what's that going to give us? We know that TE1 gives us this A1 in the first coordinate and nothing below. What's the norm squared of that vector? And you could think of a 2 norm, for example. So now we're saying that TE1 squared is the same as that norm of that vector, but that vector's norm squared is just each coordinate's absolute value squared. Suppose we start investigating what happens when we start working with the adjoint of T. What are we trying to do? We're trying to show that the matrix representation of T is diagonal if we start with T being normal. So far, we really haven't used much about the normal properties of the operator T. But if we now look at the matrix representation of the adjoint of T, we now know that that's the complex conjugate transpose of the matrix representation of T. So similarly, we can consider the matrix representation of T dagger as the conjugate transpose of the matrix representation of T. And what would that be? We had the matrix representation of T being this upper triangular. If we now transpose that, it now puts all those non-zero entries below the diagonal and conjugates those, but everything on the diagonal is real. So that we now have A11, A12 star, A13 star down to A sub 1n star, A sub 22, A sub n, this is 0, etc. This is now the matrix representation of T dagger. But now if we look at the matrix representation of T dagger operating on E1, what happens? For the specific E1 that we had before, E1 was this 1, 0, and zeros everywhere else. So this is going to pull off the first column of this matrix representation of T dagger. We now have A11, A12 star, A13 star, A sub 1n star. If that's the case, what's the norm squared of T dagger E1? Now we need to find the norm squared of that vector. And that's just the individual coordinates absolute value squared. Or we now have A11 squared plus A12 squared, etc. A1n, whoops, A1n squared. Now we can go back to what we were assuming. Now we can assume the condition or the assumption we were making on the operator t. Remember, we assumed statement A was true, which said that t is normal. And what was the first proposition we talked about today? What did that tell us about a normal operator and its norm relative to the norm of its adjoint operating on a vector? Those norms were equal, weren't they? So now we can say that we have TV squared is equal to T dagger V squared. That's proposition 720. That was true for any vector V. Well, if it's true for any vector V, let's use it on one particular vector, and let's use that on V being E1. If we now look at taking V equal to E1, we can see that this actually implies that we now have TE1 squared is equal to T dagger E1 squared. Or TE1's norm squared was A11 absolute value squared, but that's supposed to equal T dagger E1 squared, which was A11's absolute value squared plus A12's absolute value squared, A1n's absolute value squared. If those two sides are equal, what can we conclude? All of those right-hand side terms other than A11 have to be 0. Therefore, A12 is equal to A13 is equal to A1n is equal to 0. Well, if that's true, now we can actually simplify our matrix representation of the operator T. That first row was all 0 except for the 1, 1 entry. So the matrix representation of T, since T was normal, and we now have demonstrated these relationships because of this norm condition from proposition 720, so the matrix representation of T must really look like A11, A22, A23, and we have zeros to the right of A11. Now do you see what we're going to do? Now we can just keep doing this same process. We can apply it to the second row in this matrix representation of T. We can do it to the third. After we've done it to the second, we're going to find that we've now eliminated all of those off-diagonal entries in that matrix representation of T. But we can repeat this process for the other orthonormal vectors E2 through E sub n, which now allows us to say that the matrix representation of T is now diagonal. And that's what we were wanting to show. Therefore, the eigenvectors of our linear operator T do form an orthonormal basis and a diagonal matrix representation of T, which is C. So there we've shown A implies C. And earlier we'd shown C implies A, so that now we have this complex spectral theorem which equates these three statements. T is normal, we can then diagonalize that matrix. And we'll try to start picking up with the real spectral theorem next time.